So I'm excited because today we finally get to talk about some calculus. And calculus can really be broken down into the study of three different areas: limits, derivatives, and integrals. And limits are really the foundation upon which derivatives and integrals stand. In other words, we can't truly ever understand what derivatives and integrals are until we have a strong sense of what limits are. So let's talk about that today. Limits are used to describe the behavior of a function's outputs in the neighborhood of a number x is equal to c. In other words, a limit is a way of mathematically describing what a function is giving you or what its outputs are as we get closer and closer to some x value, which we'll call c. So as we get closer and closer to some x values, which we'll call c, we're asking ourselves, how is the function behaving? What are the outputs that are coming out of this function? How is it looking? And whether or not the function is actually defined at the point x is equal to c has no bearing on what the limit actually is. In order for a limit to actually exist, the function's outputs must approach the same number as you approach from the left, in other words, as you approach from the negative, as it would be if you were to approach from the right, or if you were to approach from the positive. And there are three ways to explore limits: numerically, graphically, and algebraically. And we'll go through all three of those right now. So let's start with the function below. We're looking at the function f of x is equal to x cubed minus 8 over the quantity of x minus 2. And what we're going to do right now is numerically look at the limit of this function. And really, if we kind of strip that down, what we're essentially doing is investigating its behavior near x is equal to 2. In other words, as we get closer and closer to 2 from both the left side and the right side, how is the function behaving? So we're going to take a moment right now. I'm going to have you pause the video and pretty much fill out this table on your own. And you can do this with a graphing calculator or just Desmos, or if you're really feeling bored, you can just manually input 1.9, for example, into the function and see what the output is. But let's take a quick look at the table here. Okay, so if you went ahead and filled out the table, the things that what we're looking at right now is we're asking ourselves, as x approaches 2 from the left. In other words, as we're getting closer and closer to the quantity of 2, look at the x values that precede it. We're looking at 1.9, 1.99, 1.999. So we're getting really, really close to that 2 value from the left side. And we should get these values. And if you don't have exactly what I have, it could have been a rounding issue on my part, but hopefully this kind of reinforces this idea. So ask yourself, as we're getting closer and closer to 2, what is f of x approaching? And you should see that f of x approaches, you guessed it, 12. It looks like it's getting really close to 12. Now let's look at what's happening as x approaches 2, this time from the right. So as x gets closer and closer to from the right, we should have gotten these values. Let's go from 12.001, 12.006, 12.06, and 12.61. So f of x looks like it's approaching also 12. It looks like also from the right side, it looks like it's approaching the same number, 12. So that would lead you to think, oh, so this number right here in the middle must be 12. Well, no. Really quickly, if you were to enter 2 or evaluate this function at 2, you should see that you're getting an undefined value, right? 2 minus 2 in the denominator gives you 0 in the denominator. So it's actually undefined here. So this is a really important concept. We're seeing that f of 2 is actually equal to undefined, or it's an undefined value. However, the limit of this function here, as x approaches 2, that's that notation, as x approaches 2, we're seeing that the limit of this function is equal to 12. Okay? Now, really important that we're clear about the verbiage here. What we're going to say is the following. We're going to say the limit as x approaches to is 12. In other words, the limit is 12. What we are not going to say, and I'm just going to write this in red just to reinforce this, is we are not going to say the limit approaches 12. The limit isn't approaching anything. The limit actually, I should clear out that sentence. The limit is not approaching anything. The limit is 12. The limit of this function as x approaches 2 is 12. Remember, and again, just to reinforce, this has nothing to do with the fact that f of 2 is actually undefined there. Okay, that has no bearing on what the actual limit is. So in other words, when x is 2, this function is undefined. But we can see that it is going to be 12, or in other words, the function is getting or approaching 12. So that's how we can think about this first limit numerically. Now let's look at evaluating limits graphically. So we're going to take the same exact function. So in other words, we're going to say f of x is equal to x cubed minus 8 over x minus 2. And this might be some nice review for you all the way back to chapter 2 of graphing this rational function. So take a moment right now and see if you can graph this function on your own. Okay, so if you graph this function, hopefully you found that since it's a rational function, the first thing I'm going to want to do is I'm going to factor my numerator. So this is going to be x minus 2 times x squared plus 2x plus 4. All of this over x minus 2. And hopefully you see here that we've got a common factor in both the numerator and denominator. Ask yourself, what does that mean? This tells me I'm going to have a whole at x is equal to 2. And so we can see that this function is going to look really, really, really similar to the resulting or remaining function, x squared plus 2x plus 4. The only difference being that this original function, this rational function, will have a whole at x is equal to 2. If you want to figure out where that whole is, you would just plug in 2 into our resulting function. So we get 212. And just by looking and reviewing our quadratics or our parabolas, we should see that our vertex is going to be at negative 1, 3. There's a couple of different ways that you could have done that. And let's just figure out, well, actually, we're pretty much ready to go. So I'm going to go ahead and see if it's still saved. But here's my graph. And I went ahead and just graphed that ahead of time just to save a little bit of time. But your graph should look something like this. So we've got a vertex at negative 1, 3. We've got a hole at the point 2, 12. And we know it's going to be symmetric about the axis. X is equal to negative 1. So you should get a graph that looks like this. So the point of this was not so much for us just to review graphing parabolas or rational functions, but for us to look at the limit here. So ask yourself, as x, and let me do this in a different color, as x approaches positive 2 from both the left side and the right side, the question then is, what is our function doing? What does it look like our function is getting closer and closer to? Our function's outputs appear to be approaching the point 12 or 212. So we can state the following. We can say f of x is approaching (12). Therefore, the limit as x approaches 2 of this function is equal to 12. Okay? And we're just looking at this graphically right now. Just visually, what does it look like our function is giving us as we approach a specific value? And just to reinforce this, let's try just finding another limit now. Just some other one. Let's look at negative 2. Let's ask ourselves, as x approaches negative 2, what does it look like our function is approaching? As x approaches negative 2, f of x is approaching the point 4. So we would say the limit as x approaches negative 2, so the limit as x approaches negative 2 of this function is 4. Okay? Now, you'll notice that in the example that I have in green, the limit, I should say, actually is the value or the output of the function at -2. In other words, f of -2 is indeed equal to 4. However, f of 2 is undefined. And its limit, however, is a different value. So we're seeing two instances here where the actual output or the output at the point where we're trying to find the limit has no strict bearing, I should say, on what the actual limit is. Oftentimes they will be the same, but it doesn't necessarily determine the limit itself. All right, now our final way of actually evaluating limits is to do this algebraically. So let's stick with the same function right now just so that we can stay consistent. So when we're finding limits algebraically, we use a process called direct substitution. And it's exactly what it sounds like. You are going to directly substitute your c value into your function to evaluate what the limit is. Let's do an example with the one that we did in green. So let's look at the limit as x, that's not the same color green, and that's going to be bothering me if I am slightly off. All right, let's look at the limit as x approaches -2 of this function. Okay, so the limit as x approaches -2 of this function is equal to, and the way that we're going to algebraically do this is by just plugging in -2 into our function. So if our original function was x cubed, and let me just rewrite this here, x cubed minus 8 over x minus 2. That was the original function, so now I'll scroll up. We're going to plug in -2 here, so -2 cubed minus 8 over -2 minus 2. And that just gives me -16 over -4. That's equal to 4. Okay? So the limit of this function as x approaches -2 is 4. And that matches up with what we have up here. All right? Now let's try to use direct substitution to find our original limit. So in other words, the limit as, that's a horrible looking limit notation, the limit as x approaches +2 of this function. So let's see what this gives us using direct substitution. We get 2 cubed minus 8. Again, all we're doing is plugging in 2 over 2 minus 2. And you already see where this is headed. I've got 0 over 0. It is important to note, this is what we call indeterminate form. And it's another obvious statement. Indeterminate form just simply means we cannot determine any information for what we're looking for in this current form. This does not necessarily mean that it is undefined. What we are saying, 0 over 0, is one example of something we call indeterminate form. And we'll talk about this more in this chapter. There are some other indeterminate forms, like infinity over infinity, for example. But indeterminate form just simply says, it doesn't tell us whether or not it's defined or not. It simply says, we can't answer that question in the way that this current form is presented. So, direct substitution didn't work initially for us, but what we can do is remember the following. If you look back to this graph that we have here and with the work that we showed, what I try to emphasize for you guys is that this function and this original function, those graphs are going to look really, really similar. The only difference being this function has a hole, right? Whereas our quadratic doesn't. And we're going to leverage that idea to say the following. We're going to say that this function, the limit of this function of f of x is, and let me use a different color here. The limit of this function as x approaches 2 is equal to the limit of this function in its reduced or simplified form. In other words, that x squared plus 2x plus 4. Okay? Be very careful with what I am saying here. I am not saying that this function is equal to this function. I'm not saying my original function and this function are the same. Rather, what I'm saying is that their limits are equal. In other words, if you were to find the limit of this first function at x is equal to 2, which we determined was 12, that limit, that value of 12, is the same as the limit of this function at x is equal to 2. These functions aren't the same, but their limits are. Their limits are equivalent. So what that means is to find the limit of our original function as x approaches 2, I can just simply find the limit of this reduced function that we got from the work above and say, all right, so that's equal to the limit of this function as x approaches 2. So directly substituting 2, we get the following. Okay, so direct substitution didn't work initially, but by simplifying that function, we can come up with an equivalent limit statement. Not that the original functions are the same, but their limits are equivalent. Okay, so in the next part of this video, I'm going to go ahead and formally define what a limit is and try a few more practice problems, and then also talk about when limits would not exist.